All right, so we're gonna wrap up electric fields review questions. So this is number 3. I think on page 364. That's where we left off. All right. So this question is similar to your milk and oil drop experiment. Very similar, actually. You have an oil drop that is suspended. You can see it has a mass of about 4.7 times 10 to the minus 15 kilograms. And the voltage is 120 volts. And the distance between the plates is 0.5 centimeters, okay? So we're going to figure out the charge of the oil drop. Okay, so what do we have? So we have the voltage. Change my color. All right, so we have the voltage, 120 volts. We have the mass of the droplet, 4.7 times 10 to the minus 15 kilograms. And we have the distance between the plates, which we know has to be in meters. So we're going to just convert that, 0.005 meters. Okay, so if the oil drop is suspended, that means we know that these two forces are balanced. So we know gravity is trying to pull it down, but there must be some electric force pulling up so that these two are equal. If you remember previously, the electric force can be calculated as the electric field times the charge. So we could say that the electric field times the charge would equal the mass times G. Now, if you remember, the electric field is also the same as the voltage over the distance. So we could say the voltage over the distance times the charge is equal to mg. So obviously we're going to try to isolate for Q. So Q would be mg d over v. Okay, so Q would be the mass 4.7 times 10 to the minus 15 times g times distance over the voltage. And that will give you a charge of about 2 times 10 to the minus 18 coulombs. So that would be A. If you want to know the number of missing electrons, so that would be then, remember, the charge would be N times the elementary charge. So we could say that the number of electrons would be the charge over the elementary charge. So 2 times 10 to the minus 18 over 1 point, I'm going to round up to 1.7 times 10 to the minus 9 coulombs per electron. It gives you about 12 electrons. I think it's 12, I believe it's around 12. Someone wants to just verify that.
Yeah,
Okay.
I got 12.
About 12? Okay, good. Okay, so that's number 3. All right, so let's look at number 5. It's any questions about number 3? How's it going, by the way, with the milk and oil drop experiment? Having fun with it? Going crazy?
Yeah, it's so fun.
All right, number 5. Let's look at number 5. We have number 5. We have an object attached to a thread, and we're just going to try to figure out the angle. We're not going to do the whole question. We're just going to do part of it, okay? You can probably, if I remember correctly, B is just to find the tension, which you'll see at the end that you could easily figure that part out. So the thread is on an angle. So we're going to try to figure out the angle to the vertical. Now, here's what we know. We know, obviously, we have the weight. So that's going to be the weight. And this force will be due to the electric force because it says that we have a sphere that has an excess of electrons right here, which means it's negatively charged. And there's another sphere that has a deficit of electrons, so it's positively charged. So obviously there's a force of attraction between these two spheres, which is what's going to create that angle. Okay, so FG, that's pretty easy to calculate. So FG would be obviously just M times G. So that's going to be 5 times 10 to the minus 2 times 9.8. So that ends up being about 0.49 newtons. Okay. Now Fe, we can just use Coulomb's law, K Q1 Q2 over R squared. But what we got to do first is we got to figure out what the charges are. So we need to know what, so let's say we call this 1 and we call this 2. We got to figure out what Q1 and Q2 are, okay? So it says that sphere 1 has an excess of 1 times 10 to the 12 electrons. So the charge would be the number of electrons times the elementary charge. So it's going to be 1 times 10 to the 12 times the elementary charge, which is about 1.67 times 10 to the negative 19. So that would be about, I'm just going to round it off to about 1.7 times 10 to the minus 7. Okay. Actually, the elementary charge is 1.6, not 1.7. Sorry, it should be 1.6. I think I used 1.7 last time. Okay, so so it's 1.6 times 10 to the minus 7. So that's the charge of sphere 1. The other sphere is missing 4.5 times 10 to the 12 electrons. So its charge, we work that out, would be about 7.5 times 10 to the negative 7 electrons. Again, this is negatively charged, and that would be positively charged. So we can now work out the force of attraction. So we could say Fe equals K times Q1 fix that, times 10 to the minus 7 times Q2, okay, over R squared, which is 0.12 meters squared. So that would give us approximately a force of about 7.2 times 10 to the minus 2 newtons. Okay, so this is 0.49, and this is 7.2 times 10 to the minus 2. So 0.49 and basically 0.072. Okay, so I think you would know what to do now, right? If you want to figure out the angle, you can do inverse tan, right, of opposite over adjacent. So if you do that, you will get an angle of approximately about 8.4 degrees. Okay. Oh, I think I need to bother you with that. I think you know how to do that. And obviously the B, which I don't have here, but you can easily work it out. B would be the force, the tension. Obviously, it's going to be the sum of the squares of the two components, right? Okay. Questions about that? Okay, so let's look at number 4. Number 4, page 368. Number 4 is not very difficult, but it could be a little bit tricky if you don't kind of understand what this means. So 2 electrons are held at rest at a distance of 10 to the minus 12 meters. So if I have an electron here, an electron there, there is obviously going to be a repulsive force. And what that repulsive force is going to represent, we can translate that into some sort of a potential energy. If you remember, we can work out the electrical potential energy like we did with gravitational potential energy. If we, think of it as this, it's the same method. So instead of it being G M1 M2 over R, it would be K Q1 Q2 over R. So there's an electrical potential energy between these 2 electrons, because you could imagine if you were to release them, they would fly apart. They would move off in opposite directions. And that potential energy would then be converted into kinetic energy. Okay, so then what we could do is we could figure out what the potential energy is for these 2 electrons when they're at rest. Okay, that's easy. So we can just say K is 9 times 10 to the 9 times Q1 times Q2. So obviously the charge is the same over that distance. So the potential energy for my electron pair, would be about 2.3 times 10 to the minus 16 joules. Okay. Now that, that's not that difficult in terms of an equation. What's the tricky part is the follow-up. What do you think is meant by the kinetic energy and speed at some large distance? What do you think is implied by that statement? Anyone want to guess? Looking in the chat. Yeah, very good. Oh, yeah, very good. It means the potential energy would become 0, which means that potential energy would simply become the kinetic energy, right? So we could just simply say then that this potential energy, which becomes 0, becomes all kinetic energy, which we know is 1/2 mv squared, right? But it's the potential energy, sorry, it's the kinetic energy of both electrons. So keep that in mind. It's not the kinetic energy of one electron, it's both, 1 and 2. So we can do this because 2.3 times 10 to the minus 16 is equal to 1/2. We can just combine them and say 2m v squared. So we could say that, we can simply say 2.3 times 10 to the minus 16 is going to be equal to mv squared. So we can say v squared would be the square root of 2.3 times 10 to the minus 16 over m, mass of the electron, which is 9 times 10 to the 31. So then that would give you a speed of approximately 1.6 times 10 to the minus 7 meters per, sorry, not 10 to the minus 7, 10 to the 7 meters per second. Okay. All right. I think so that really the tricky part in that question is, large distance means, like as Maya said, potential energy basically is 0. So it's all converted kinetic energy. You just got to keep in mind it's the kinetic energy of both electrons. So you have to add up their masses. And so that would be really the only tricky part of that question. Otherwise, mathematically, it's not that difficult. Okay, number 5. Okay, what is the potential difference required to accelerate a positively charged Deuteron? Now, Deuteron is, does anyone know what that is? Uh-oh, why's my pen not working? Anyone want to guess what that is? It's a hydrogen isotope. It would be H2. So it's got a proton and a neutron. Okay, so what is the difference required to accelerate a positively charged deuteron from rest to a speed of 5 times 10 to the 6 meters per second? Okay, so here's what we also know. Because it's hydrogen, we know it's got 1 proton and 1 electron. So we know. So if it's positively charged, that means its charge is just simply +1. So we know we can actually work out what its charge is. We could say Q would simply be the elementary charge of that missing electron. So it would have a charge of plus 1.6 times 10 to the minus 19 coulombs. That should be big Q. That should be little q, sorry, little q. Okay, so it's that's its charge, okay? 1.6 times 10 to the minus 19 coulombs. This is missing that 1 electron. Okay. Like previous, we can say that the the kinetic energy would equal the electrical potential energy. Now, here's the thing. Here's what we know from previous time we talked about voltage, because we're looking for the potential difference, right? So that is the voltage. And if you remember, the voltage is the amount of energy per coulombs. So we could also say that the electrical potential energy will be the voltage times the charge, because if volts is joules per coulomb and we multiply that by coulombs, you would get your electrical potential energy. So this will be the same. So we could say the kinetic energy is equal then to the voltage times the charge. That way we could rearrange and solve for that voltage, which is the potential difference. Just be careful here, because you have V on the left side and you have V on the right, but they're not the same thing, right? So one is voltage, one is speed. Just keep that in mind. I don't know if you want to make one a bigger V or whatever. Just keep that in mind. Okay, so the voltage, I'm going to draw it as a bigger V, would be 1/2 mv squared over the charge. So let's change that. Okay, so the voltage then would be 1/2 times the mass of this particle. That's the mass of 1 proton and 1 neutron. Remember, they're about the same mass. Times its speed squared. Over that elementary charge is missing 1 electron. That would give you a voltage of about 2.6 times 10 to the 5 volts. All right. Any questions? Okay, 2 more, and then we're done. What speed will an electron at rest reach as it passes a hole in a positive plate that is 0.12 meters from a negative plate? So imagine 2 plates, and there's a hole. Oops, erased everything. So maybe there's a hole, okay? And we have some electron, and it's going to go from the negative side to the positive side, and it's going to travel through this hole, okay? It's going to pick up speed. So here's what we know. We have the voltage. We have the distance. And we know it's an electron, so we have the charge. Now, in this case, the distance actually is irrelevant. We don't need the distance because what we need to think about here is just energy. We're going to convert the potential energy into the kinetic energy, right? Just like we did previously. So we could say EK is going to equal the electrical potential energy. Now, remember, voltage is joules per Coulomb. So the voltage times the charge would give you the energy. Therefore, the kinetic energy would equal V times Q. So if we want the speed of that electron, we could say V would be the square root of voltage times charge over M times 2. Okay, so if we work that out, square root of the voltage, so the voltage is 1200 volts, times the charge of the electron, times 2, over the mass of the electron. Okay, that would give us a speed of about 2.1 times 10 to the 7 meters per second. Okay, all right. One more question. Anything so far? Is my writing getting any better? Or is it still like pretty awful to look at? Must be
It's
getting a
okay,
little bit.
sir.
Yeah, it must be getting a little bit better, right?
Yeah, sure.
Tavine says it's getting worse. Tavine, you are the worst. Never mind my writing. Okay, last question. All right, an electron is accelerated through an electric field with an initial speed of 1.2 times 10 to the 6 meters per second. What is the work done as it traveled 2.5 centimeters? So we're looking for the work done. Okay, we know from grade 11, work is force times distance, right? Now in this case, the force would be the electric force. Now, from previous, we said that the electric force is the same as the electric field times the charge. Okay, so that means the work would be electric field times the charge times the distance. So the electric field is 2.5 times, I'm missing the exponent. I think it's 10 to the 2. Should be 10 to the 2. Yeah, it is 10 to the 2. Okay. 2.5 times 10 to the 2 newtons per coulomb times the charge of the electron. 1.6 times 10 to the minus 19 times the distance that it travels. It's got to be in meters. Okay, that would be the work. So that would be about 1 times 10 to the minus 18 joules. And then if, what is the work done? I think the follow-up question would be to figure out the final speed. So, you know, I think you should be able to figure that out, right? Obviously, the work would be the change in kinetic energy, and then you could use that to figure out the final speed. So I think you can do that on your own. So let me stop there. Okay. Let me stop the record button. And then if anyone has any questions, I'll take questions.